Hi, I'm Pui from University of Bristol. Here I'm presenting our work that applies the popular deep learning technique, which is CNN, to detect ground deformation in the built environment using INSAR data. This is a cooperation between University of Bristol and University of Leeds, funded by NERC Digital Environment. This work is based on our previous work that successfully used machine learning to detect fringes in the wrap interferograms. The left image shows our framework that trained AlexNet to classify volcano deformation and background. The incoming interferogram is divided into overlapping patches run through CNN model to produce the probability map as shown in the right figure. The high probability locate at where fringes are. Here, we transfer this model to detect ground deformation in the UK, which are caused by different sources. A bit of recap about CNN works. It captures spatial relationship between neighboring pixels through convolution operators as its name. When we look at the interferograms here, at the volcano, there are dense pixels and the fringes have very strong features for classification. However, when we look at the signal we want to detect ground deformation in the UK, like the velocity map in London here, the data are sparse and there are gaps between pixels which is not suitable for CNN. Moreover, as it uses different techniques to acquire INSAR data contains spiky noise. We also face other problems. We don't have good labeled data, and what we want to detect appear to be very slow and localized. So we tackle these problems with three proposed techniques, which is spatial interpolation to deal with sparsity, using synthetic data for training, and apply overlapping technique to detect slow motion. For the first technique, we solve spatial interpolation using inverse problem. Following the first equation, we want to find x from the observed signal y and the subsampling matrix S. This is done through the matrix completion technique. The algorithm tries to minimize the cost function shown in the second equation below. It solves low row rank matrix using SVG and applies soft thresholding to reduce some noise. This is an example of results. The top left is the low sparse data, and the bottom left is the interpolated result from the traditional triangular method. It enhances spiky noise compared to our method on the top right, which is a lot smoother. The wrapped version shows clear that the result from our method has clear fringes that are suitable for detection by CNN. The second technique proposed here is using synthetic examples to train CNN model. We produced two models here, the point source for coal mining subsidence and the tunnel model. The top row from this figure is unwrapped signal, and the bottom row shows the wrapped version. We combine deformation with turbulent atmosphere, then subsampling and add some spiky noise following the characteristic of the UK dataset, and finally interpolate with the matrix completion. And the last proposed technique is overlapping. The side on this equation represent phase, and then we multiply this phase with some gains and rewrapping it. The figure and the plot show how CNN can detect the original signal with different level of noise. And then when some gains are applied, the signal have more fringes and CNN can detect at lower velocity. We ran two case studies at Normanton and London. In Normanton, the point source model can detect some subsidence areas caused by coal mining as shown in the probability map. And in London, the tonal model detects the subsidence from the constructing the trend line in London. Now we run the detection method on the whole UK data from SatSense, which is 10 meter velocity map. There are more than 90 million data points, and there's more than 3,250 full HD TVs combined. So to automatically process this large velocity map, we divide it into several 2,500 by 2,500 maps, defined by the limitation of the memory required to process the spatial interpolation. Figure shows the center of locations where CNN detect them as being deformation. Results here show coal mining regions in area A to F, A at the Midland up toward Leeds, B in South Wales, C Northern Castleford, D in Stoke-on-Trent, E in North West Leicester, and F in the Northumberland and Durham. In the northwest of Wales at area I, the method detects subsidence from some form of slate quarry. And an example that area G show uplift from groundwater rebound after a construction of the cross rail finished. So we analyze our detection performance by plotting a histogram of the deformation rate against probability output of the detection method. Several areas have both high velocity and high probabilities as expected, like area D1 in the Stoke-on-Trent and Q2 in Lake District. The CNN assigns high probabilities to some area with low medium velocity because of their spatial patterns, for example area D1 and Q1. The CNN also assign low probability to some area as well with a high velocity because they do not have the appropriate spatial pattern, which it fringes in this case. For example, in Bristol City Centre has several pixels with velocity more than 5 mm per year, which are caused by spiky noise. From the histogram in previous slide, so we set 3 thresholds at 3, 4.5 and 5 mm per year to classify slow, medium and fast deformation, and apply a thresholding technique just to compare. So yes, compared to our proposed method, the thresholding technique generates significantly more positive points for experts to further investigate. So total it's more than 4,000 positive points compared to only 258 of locations using the CNN. There's some limitation here. So landslides with significant horizontal motion were detected in the south of Kirby, Stephen, but the method didn't detect the landslide and the black vein in West Norset. But not so surprised, but the sinkhole cannot be detected at all here. This is because their spatial characteristics are too similar to noise. So we plan to apply both time series analysis and spatial temporal 3D analysis in InSAR data for future work. This obviously to give more information for ground deformation to be detected, as you can see from the plot to show what happened at the time series, that something changed here. So in conclusion, we demonstrate the feasibility of using a CNN approach to detect ground deformation in urban and semi-urban areas in the UK. We analyze characteristics of the data and propose several adaptations to the previous developed deep learning methods. Using the metric completion to overcome the sparse and uneven measurement distribution and simultaneously reduce spiky noise. Synthetic examples based on point source and kernel are used for training due to the lack of the real signal and deformation. And finally, overlapping and phase shifting techniques are employed to enhance features and hence reduce the detection threshold. So using a probability threshold of 0.5, the method produces more false positives than false negatives. However, the probability value and the size of the detected area can be employed to parallelize further analysis. So you can read more information about this work from the reference that we give it here. Thank you.